theta is the angle between the normal to the surface and the electric field. Or in my fishing case, the normal to the net and the water flow, the velocity of the water. It's the angle between E and A is what it is. This is a dot product, right? If you can write it this way. And so my electric field points one direction, and my surface, if my surface is at an angle, then the area vector, which points in the direction of the normal to the surface, and theta is the angle between them. And this is that's my surface, right? Lines now. And what this first box, the mystery box, inside of this box, there's some charge or charges. And they've given us some electric field lines indicated around the outside of the box. And your job is to guess what the charge distribution looks like inside that box. Is there one charge or multiple charges? Are they positive, negative? What charges inside that box would create an electric field that has this shape of the given points outside the box? You understand? Okay. We have a volunteer. Okay, thank you. Anybody have anything different? Everybody has this? What do you think? That seems to be pretty good. What would happen if I have a plus and a minus? What would the electric field look like? It comes out from the plus and it goes to the minus. So it would do something like that. And it would come out this side and sort of keep going. And one would come in from infinity on this side. And one maybe comes up like this and loops around in that direction. And if it came out this way, it would loop around in this direction. And if it came out that way, it would loop around in that direction. So where are the locations of interest here? We've got a point right in the middle of the box, close. So right here, we would expect the electric field to point what direction? To the left, and it would be fairly large, right? We draw a long arrow there to represent that because we're close in here. These lines are pretty close together. So we'd have an electric field that looks something like that. But up here, what would we expect? A little further away. Same direction, but a shorter arrow, right? It drops off as we move away. And then out here it points in this direction, and out here it points in. So I think we've got this one. You okay with that? We've got the arrow at the bottom there coming in. To the left, long. We're further away. To the left, short. And these two arrows are basically in the direction we would expect from this charge distribution. Good? All right, let's do the next one. B. They're all about the same, I think. You want this light on or off, Pam? We have agreement? You like that? Same again, right? We're going to get from the positive to the negative. So if we're equal distant on the left and the right, it's going to be pointing up with the same length arrow. And if we're at the top, it'll be pointing down. And over here, it'll be pointing down. And if we're kind of at a funny spot over here, it'll be pointing something like that, right? The electric field points tangent to the field line. OK? How about C? Somebody want to do C for me? OK, we have agreement. A single positive charge in the middle probably would match this very nicely. The electric field lines would come out in all directions. How about D? What do you think for D? What should I do for D? A whole line of them, right? Maybe something like that. Some kind of positive rod or... And then what would the electric field look like? In the middle, it would be coming out straight. And then it would start to curve out a little bit. Something like that. Which kind of matches. The longer this rod is, the more these lines here will straighten out in the middle, and the edge effects will be less and less. As we make this rod longer and longer, we become more and more uniform with the field lines coming out perpendicular from the rod. When it becomes infinitely long, all the field lines are perpendicular to each other. We don't get any edge effects. OK, what's the point of this whole exercise? The point is that we can look at the field and learn something about the charge distribution right inside the box. There's a link between what's going on inside the box with those charges, how they're distributed inside the box, and what the field is, right? They're creating that field outside. So because there's this link, we should be able to tell something about the electric field by the charges inside and vice versa. And that's what Gauss's law tries to do. It tries to link the electric field coming out of the box to the charges inside the box. OK? So let's, why don't we take a 10-minute break, and then we'll start on the Gauss's law worksheet.